Hello, we're at Energy 101, and today we're going to talk about the characteristics of electric power. We reviewed the different technologies that we use to generate electricity, and now we're going to look at the characteristics of those technologies once they're in the field or new ones that are being installed. So the technologies that we mentioned already, and we'll look at quickly today to look at the appropriate efficiencies and the carbon emissions that are associated with the fossil fuel plants. Coal-fired steam, Rankine cycles, we call that. Natural gas turbines are simple cycles where it's a simple gas turbine and the exhaust heat is exhausted to the atmosphere and is lost. The natural gas turbines combined cycle where the exhaust is still hot, of course, from the turbine, is used in a boiler to boil steam and is put through the same cycle that a coal-fired power plant, but this time rather than using coal to boil the steam in the Rankine cycle, you use the hot exhaust gases from the gas turbine. It costs more, but that's essentially what's almost everything in the gas turbine area that's being installed today are the combined cycle gas turbines. The nuclear plants are steam cycles, and they boil steam by the nuclear fission process. The hydro that we mentioned, wind turbines that take kinetic energy out of the air and convert it to a spinning shaft that can turn a generator, and solar photovoltaics, that's magic, what we call direct energy conversion. It takes the solar energy, the photons in the radiation from the sun, strike a semiconductor surface, and that produces electricity directly from the chip with no moving parts. And then solar thermal, where we concentrate the sun's rays onto a central spot and heat or boil water in order to, again, run the steam cycle, just as a coal-fired power plant and as the nuclear plant does. It's just a different source of thermal energy, this time being the sun that heats the boiler as it concentrates the sun down to a very small surface. So let's look at the efficiencies first. The efficiencies are particularly important for the fossil fuel plants, and if we look at coal and biomass, because biomass is just used in the same way as coal to fire the boiler, then the new plants are up a little above 35% on peak efficiency. If you look at the installed base of all the steams of coal-fired plants out there, it's around 34%. So that's throws away about 2 out of every 3 BTUs that the coal gives off when you burn it. So it's a big source of heat that's thrown away in general to the rivers or to the atmosphere. Natural gas, a simple cycle gas turbine, I've already mentioned that just is a gas turbine without recovery of the exhaust heat in a steam cycle. New plants, you can get around 35%, and these are approximate numbers, but the installed numbers are actual data, field data from the Energy Information Agency. Is about 29%. 29% for the simple gas turbine cycle. And then we have the combined cycle. They will go to 55 or even up towards 60 operating in a steady state at their peak efficiency of operation, which once you get in the field, you don't operate it always at that steady state peak efficiency condition, and they throttle up and down, and you have to get them warmed up, and plus some of the technology, of course, the plants in the field are older technologies that have been installed 10 years or 15 years ago, and those are around 45%. So you can see that the combined cycle gas turbine utilizes natural gas at a much higher efficiency than the coal does, which is only 35% versus 45% for the natural gas combined cycle. That's one of the reasons that you have lower carbon emissions. Nuclear power, as I mentioned, is just another heat source for the coal-fired steam Rankine cycle that boils the steam rather than coal, and that is around 35% new plants and around 30% installed plants. It's hard to get data on those numbers because nobody worries too much about the fuel efficiency for nuclear plants because the fuel is very cheap. It's not even close to the fuel cost to run a coal plant or a natural gas plant. But of course the plant's more expensive to build, and you have to amortize that capital cost and interest on the money that over the life of the plant for the kilowatt hours that is produced. And going on for the renewable power plant technologies, hydro actually converts about 90% of the energy in the water that is behind the dam due to the depth of the height of the dam. The water at the lower part of the dam is under high pressure, and that moves through a water turbine and spins the shaft and produces electricity. That's not a heat cycle. That's limited by the second law of thermodynamics in that case. It is limited by the first energy that you can't get more than 100% because you can't get more energy out of it than you put in, than the water has when it goes in. Wind turbines, of course, extracts kinetic energy out of the wind, and that extracts about 45 to 50% of the kinetic energy that's in the wind that's passing through the turbine blades is converted into electricity. There's a theoretical limit to that. You can't go to 100%, even though it's not a heat cycle. That's limited by the Carnot efficiency, we call it, or the heat equation for the second law. But the Betz limit, no matter what you do, you get rid of friction and do everything in an ideal manner, is 58%. So you can't extract more than 58% of the kinetic energy in the wind and convert it to shaft power. It's just the limits of laws of nature. Then we get to solar. There are two kinds of solar technologies, photovoltaic technologies, in addition to the solar thermal technology that's we'll get to in a minute. But you have the photovoltaic silicon and the photovoltaic thin film. The silicon chips, thin wafers, polycrystalline, will get 15 to 20% at the peak radiation efficiency at noon, typically, and convert it into electricity. So that's 15 to 20% of all the sun's energy that's falling on the module, the collector module PV module will be converted to electricity under the best conditions. Thin films are much lower, but these can be done out of plastic and can be flexible, and they're much cheaper per unit area to produce than the thin wafer polysilicon and polycrystalline. But the efficiency of converting the sun's energy that hits them is lower, so you have to have on the order of twice as much area of the thin film collectors as you do the silicon collectors. So that's just the nature of the physics of the thin film technology. And it's really in its infancy. It's really coming on strong, though, and where it'll end up and how it'll compete is yet to be seen. And then the solar thermal, I mentioned the concentrating collectors, the power towers, or the troughs that we looked at and talked about the technologies there. Those will convert about 25 to 35% of the solar energy to electricity, and again, it goes through the steam cycle, which limits it to about 35% because of some second law of thermodynamics limitations, as well as the practical limitations of materials and friction and things. So those are the fuel, energy source to efficiency ranges of new technology. And by the way, I didn't talk about the difference between installed technology and the new technology with renewables, because renewables so young, basically there's not much difference between what's already out there and what's being installed, because it's growing so fast. The installed base is basically in this range, which is where the new technology is too. So that's the reason we don't have installed versus the new technology. Now, what about CO2 emissions? An important characteristic of any power plant this day and time are the carbon emissions or CO2 emissions, and that's only a significant factor where we have fossil fuel plants. So I look at just coal and natural gas, and the steam cycle puts out, and on the right-hand side I've got CO2 emissions in units of pounds per kilowatt hour, and in parentheses, grams per kilowatt hour. So in the steam cycle, coal steam cycle, burning coal, you produce about 2.2 pounds of CO2 per kilowatt hour that's produced. That's in the field operation. Again, it comes from Energy Information Agency data right off their website. That's about 1,000 grams per kilowatt hour of carbon emissions per kilowatt hour in the metric system. If it's new technology, it's not much difference, 10% or so better, at 2 pounds per kilowatt hour or 900 grams per kilowatt hour. Not much difference there between installed and new for the steam cycle. The steam cycle has been around for over 100 years, 150 years really, and the original steam engines that used on the boats to power boats was one of the first broad application of the old steam engine. It's essentially the same technology. And so we've been working on it and trying to improve it for 150 years, and it's pretty well asymptote the efficiency that we can get out of the coal-fired steam cycle. When we go to natural gas, and I've only looked at combined cycle natural gas here because that's the dominant new technology that's been installed for the last several years, as well as the new stuff that's being installed now. There's very little, I don't know of any simple cycle gas turbines. I'm sure there are, but they're very, very few. Almost all of the plants being installed today are combined cycle, and almost all of the electricity generated from natural gas is coming from combined cycle gas turbines. As you can see, the carbon emissions from the natural gas combined cycle gas turbine plants is about less than half of what it is for coal, both for the installed and the new. It's about 0.96 pounds per kilowatt hour, or 440 grams per kilowatt hour, and the new is about 0.8 pounds per kilowatt hour, or 350 grams per kilowatt hour. So that's the reason that from a global warming viewpoint, and if you're worried about carbon emissions, where so many companies are idling or shutting down totally coal plants, particularly the old ones. Some of these plants that are in operation today were built in the 40s and 50s even, and are still operating. So they're shutting down a lot of the old, very old coal plants, and efficiencies are lower, and they're more expensive to maintain because they are so old, and replacing them with combined cycle gas turbines, particularly today with the cheap natural gas that we have. How long that will remain with us is a $64,000 question. Anybody's guess in some respects. It'll certainly, we expect it to stay down for the next year or two anyway. But that's the efficiency and carbon emission characteristics, which are the principal characteristics we're interested in these electric power plant technologies. Thank you.